In the previous video, we started working on finding the second order derivatives, partial derivatives of this function in example 1 here. And now we want to find the mixed partial derivatives. And so now, because I've taken the derivative with respect to x, I can now take that guy and take its derivative with respect to y. So the innermost, when you're using the f notation, the innermost variable is the first derivative that gets taken. And as you take more and more derivatives, we start to stack them onto the right. So if I now take the derivative of this guy with respect to y, well, it doesn't depend on y, so its derivative will be 0. Similarly here, I can take f sub y, take its derivative with respect to x, and this guy doesn't depend on x, so its partial is 0. And the one thing that we should note that's going to become an important tidbit here is that these are equal. And that will be true in general. The two mixed partial derivatives are equal. They're going to be the same. If you take the derivative with respect to y first and then x, you'll get the same answer as if you take the derivative with respect to x and then with respect to y. So we really only need to find one mixed partial derivative, and we automatically have the other. So let's just verify this. Let's just see it for a case where the second derivative doesn't become 0. So let's look at f sub x of this function. So to take the derivative with respect to x, I will get 9x squared y to the 4th. The partial with respect to y will be 3x to the 3rd times 4y to the 3rd, which will be 12x to the 3rd y to the 3rd. And if I take the derivative of f sub x now with respect to y, I will get let's see, derivative of y to the 4th is 4y cubed. 4 times 9 is 36. So I'll get 36x squared y cubed. And if I do this for f sub y and take its derivative with respect to x now, I will get, let's see, 3 times 12 is 36. Subtract 1 from the power. This is a constant multiplier. And we again see that these two guys are equal. This can be proven. It's not a proof that we want to get into here, but you can really just compute one, and then you can say, well, the other one's f sub y x, given that I know f sub x y is going to be identical. The tricky part is thinking about this. We already described in the beginning of our first video why the second derivative has to do with concavity, and it tells us whether the slopes are getting bigger or smaller. And that in turn tells us whether we should expect something that's concave up or concave down. But the mixed partial derivative is a little bit more tricky to think about because we're looking at so if we look at the mixed partial in this fashion, so this guy here that we're describing is actually the partial derivative with respect to x, then taken with respect to y. So that's another way we could write that. But if I write it like this, I notice that the first derivative that gets taken is with respect to x. So we can think about this as the slope of f in the x direction. So what is happening to the z value as I increase x by 1? But I want to know, if I think about this right here as that corresponding slope, I want to know what's going to happen to that slope if I were to increase y by 1, or if I were to increase y by even an infinitesimally small amount. So maybe what I would observe is that the function, if I kind of thought about this as a couple of cross sections. So let me try to sketch a three-dimensional graph here, for better or for worse. And what I want to think about is, here is, let's say, my x-axis, my y-axis, and then f of xy. Or you could call that z as well. So maybe back here, the slope or the cross-section, let's say for a fixed value of y, maybe what I observe here for this value of y is if I look at that cross-section of a function, maybe what I'll observe is something like this. Maybe that cross-section will be parabolic, right? So at any given point, let's say that what I'm really interested in is at this point right here for this value of x, I can see that that slope of that little line segment is going to be positive. So right there, if we kind of think about that slope is positive. But what happens to that slope if I increase y by a little bit? So this green line right here, this is what we can think of as df dx, right? Oh, I'm sorry, so this would be a negative slope, because if we're moving positively in the x direction this way, this slope points downwards. That means the trajectory of the curve is going down. But I want to know what happens to the slope at that point right there if I were to increase y by one more unit. So if I increase y by one more unit, let's say that's here, and again I look at that cross section, maybe what I'll actually observe is that that three-dimensional function changes a little bit. Maybe it starts to look a little bit more like this. And it's maybe changing more. It's almost like sort of maybe over here it's a really tight curve, and you can kind of almost see this like cone type shape to those cross sections. And at this point now, at that same point where I was looking at the slope, I want to ask what happened from this slope to this slope over here. So this slope over here is a little bit more flat. And so what I notice is maybe if this slope is -2 and maybe this slope is -1, so we can say that if I increase y by a little bit, and I'll put that in quotes, little bit, then df dx goes from -2 to -1. So that means the slope, i.e. the slope in the x direction, is less negative. So that's all we're doing here is we're looking at slopes and we're comparing those slopes for different values of y. We could do the same thing for the x direction. We won't do that here, but imagine that we could look at this same graph, but instead of holding a value of looking at two different cross sections by changing y by a little bit, we could imagine these two curves going horizontally and them at different positions in x. Why don't we just go ahead and take a look at it just to see and make sense of this a little bit better. So here we have, again, the x, y, and the f of xy axis. And let's say what I want to look at is how does the slope in the y direction change? How does that change? Here's my change operator. What is the change in that slope in the y direction if I change x by 1? So here in this case, I want to look at the df dy. So df dy holds a value of x constant. So let's say that's the value of x that we're holding constant. Okay, and so right across here we can draw a dotted line to indicate that that's a value of x. And maybe the cross section we see there, let's just draw something a little bit more, something different than the last example. It might look something like this, let's say. That's the cross section for that particular value of x. So if I draw maybe a little bit of a change in x, and again I look at that cross section, maybe that cross section actually looks like this. Okay, so these are, notice that these are, this particular concave down piece is a little bit further towards us. This one's a little bit further back. Actually, let's make this a little less overlapping. Let's say that this actually maybe looks like more of a sine curve cross section like that. And if I look at a specific point on this curve, let's again say that maybe that point is, oh, I don't know, here. So let's look at that point right there and then compare it to that same point on the next curve over. So what I would observe here is if I were to look at df dy, I'm asking what happens to the value of z if I increase y by a little bit? Well, I can see that that's a slightly negative slope right there. So I would say that df dy right there is negative. And maybe let's give that a number. Let's say that that's -1. But then if I move over, if I change my value of x, so if I look at that same slope, but for a slightly different value of x, then what I may notice is that slope right there is actually maybe 0. So we'll say that that is actually the peak of that little curve, and we'll say that its slope is 0. So what would I say about that? Well, if I increase x by a little bit, again, what does it mean little bit? We mean something infinitesimally small. Then the slope in the y direction, df dy, goes from -1 to 0. So that means that the slope in the y direction is less negative again. So I won't write that, but i.e. the slope in the y direction is less negative. So up here, what I would observe is that df dx, and the change in that, if I increase y by 1, for our particular example here, because that slope increased, I could say that this mixed partial is bigger than 0. If I increase x by a little bit, df dy goes from -1 to 0, so I can also say that this has increased, and therefore I could say that that mixed partial derivative for this drawn example also is positive. Let's now take a look at a computational example. Here I have a table of values, and I want to estimate the two mixed partial derivatives at the point 1, 2. So at the point 1, 2, my focus is this square, or this rectangle right here. And so the first thing I'm going to do is I see the first derivative here is in the x direction. So if I first look at f sub x at the point 1, 2, I'm asking what happens to the z value, or what's an estimate of what happens to the z value if I increase x by 1. So here's my x values, here's my y values. So if I increase x by 1, I see that the change is from it goes to 9.6. So the change there is going to be an increase of 1.6 units. X, however, increased from 1.0 to 1.1. So 9.6 minus 8 is 1.6, divided by 0.1 is 16. So if this same change persisted, if x went up by a whole unit, I could say that the z value would go up by 16. Now, what I want to ask is, how does that slope change if I increase my y value by a little bit? Okay, so now to estimate the change of how that slope of 16 changes for a small change in y, well, I can create a small change in y by going from 2 to 2.2 and asking that same question. So how does f sub x at the point 1 for x, comma 2.2 for y change? Well, here my z value goes from 10.65 to 12.88. And again, my x value goes from 1 to 1.1. So I'm still looking at the same slope, at the same value of x, but I'm increasing y by a little bit. That comes out to about 22.3. So what do I notice? Well, I notice the slope in the x direction increases from 16 to 22.3. I didn't write that again. So this represents an increase in df dx. And, well, how much of an increase? Well, now I want to estimate that. I want to say that the change in that slope, if I increase y by 1, and my point of comparison is 1, 2 is what the location that I'm at, well, I'm going to look at the change in these two slopes. So it went from 16 to 22.3, and the value of y changed from 2 to 2.2. So 2.2 minus 2, that's my change in y right there, my change in y. These guys are my df dx's. This is df dx, and this is df dx, but they're for slightly different values of y. And that comes out to 31.5. And in the next video, we'll talk about that.